Yes, thank you, everyone. This is Jun Wang from Electrical and Computer Engineering. I'm so glad to be the first speaker and talk in the new year. And today I would like to talk about some research my lab has been doing in recent, 3 years, and talking about how to enabling high performance sampling for big data processing and big learnings. And here is my information. And before I start the talk, I would like to introduce what we have doing in the last like 15 years, from my research lab called Computer Architecture and Storage Research, Storage Systems, CAS. And we are doing a lot of, research work trying to achieve fast data processes and resources sharing with cost and energy efficient management and for all different kinds of memory hierarchy and storage architectures in all kinds of computers like mobile devices, desktop, laptop, single servers, and cluster machine and supercomputers. And we also promote, massive data processing with interdisciplinary scientists to advance the knowledge discovery in the domain, in different domains. And we work with the different national lab in DOE and help them to accelerate their data processing. And we have published more than 150 papers, in the last 10 years. And the main deliverable products we do is we develop a couple of open source prototype systems, software tools, and we work with the domain scientists that led them to make their software run better. And we distributed some open source software to the open research committee for them to use. And recent years, we start looking at some, co-hardware software design. We develop some, hardware system prototype and platforms, and trying to help the research communities. And we graduate about 13 PhD, 20 masters, and a lot of undergraduate students. And for the research. And if you want more detail about myself, and this is the URL link you can visit. And the main topic I'm going to address today is our 3-year National Science Foundation projects, and we are developing a highly efficient and accurate approximation system for warehouse scale computers like Hadoop clusters and Google clusters, and with kind of new sub-data set distribution aware approaches. We are already in the big data, and it's nothing secret. But a lot of people know, and surprisingly, huge of data generated in every second, right? And 98,000 tweets, 700K, status updates, 11 million instant messages. Believe it or not, one user, single user, and mobile users smartphone user is going to generate 40 exabytes every month. Okay, just every month. Imagine how big that is that. And we have 5 billion people, right? Smartphone users on this planet. And if you, do the simple math, it's going to be oceans. Okay, and one major techniques to help process this joint data is called approximation techniques. One of the approximation techniques people use is called sampling, right? And given a large data population, and if you're trying to develop make some good predictions, and it's going to be time consuming, take several days, weeks to get your estimated results. So the current scientists are trying to figure out why, instead of going through the full scan of the whole data set population, why don't you just analyze a sample, like for example 1% of the sample data set, that will significantly reduce your data amounts, right, to be processed. So that's a simple idea, and people already promote these things in a lot of different areas. But it's simple to say that, but from system engineering's perspective, computer science perspective, it's difficult to implement. And the challenge is really working on this trying to make a good trade-off among the data size, how big data you want to really process, how much sample you are going to address, right? And how accurate about your results. What is your estimate accuracy? How that far away from your actual results, right? And then how do you want to get the fast response, right? So all these responsiveness, accuracy, and data science is we are trying to make a nice strike trade-off among these three dimensions, right? And more complicated things is if you look at the actual data processing platform, which we typically look at is Amazon cloud, different kinds of Hadoop computing platform, 100 nodes machines. And if you look at this diagram, we did the experiments is saying, if you simply just populate real Amazon data sets on this any common computer or cluster, data clusters, and the distribution is very skewed, meaning that some data are saved on only small number of machine, which may be interesting to you. For example, and Amazon, the websites, there's tons of the data sets, all kinds of reviews, including the books, right, movies, the songs, records, scientist review, all this kind of reviews. But if someone is only interested in the movie review, I just want to know, what is a recent movie, the users' comments and ranking on the movie related, and I try to find some idea what is the best movie I may get. You're only interested in the movie, right, review. So if you look at this actual, data distribution saved on this data cluster, and the movie records, unfortunately, only are concentrated on a small, like 10 machine instead of the 100 machines. So that will create a big issue if you are not able to process these movie records quickly. So to attack this problem, we develop a new solution. We basically trying to get the distribution ahead of time, and then we trying to support any arbitrary query, no matter what kind of query you want to go. We just want to make it I/O efficient and integrate into the current Hadoop platform, make it work. And this is the whole overflow of the of these projects. And the simulation data, sensor data, IoT data, social network data is going to be the real-time data stream come to this big data massive storage platform. Then we're doing the sampling, apply different kinds of sampling algorithm on these to reduce data sets. And then we're going to do the proximate computing and with our integrate into the current parallel processing stuff and get our estimates. We publish our paper in the very large database and some transaction journals, and get 20%. The speed up is 20 times. And a follow-on research projects on the NSF, actually is a new one. I launched this last year. I'm the single PI, is trying to use the hardware, the machine learning, deep learning techniques, leverage the current GPU machine, right? GPU resources to further accelerate the I/O processings. And nowadays we have all different kinds of acceleration hardware, FPGA, GPU, how this rich acceleration hardware can be leveraged, right, to further speed up the big data processing. That's a very interesting to investigate. We carefully investigate some of these deep learning algorithms. We think out the unique characteristics about the AI model, deep learning model, just specific for the I/O workloads, right? And we think out some I/O net techniques, trying to develop a customized deep learning model for the computer massive storage systems. And given this model, we also look at some specific problem when we define and when we implement these computer storage system like indexing, prefetching, caching, garbage collection, and how these different kinds of deep learning algorithms can help to optimize these massive storage systems. And we also look at some intercommunication stuff. And last another project and is a teamwork. And I work with other two co-PI, Dr. Jisan Guo and Dr. Amaro Awad, and we cover different kinds of expertise, systems, computer architecture, hardware, security. Guo is on the algorithm side, and we're trying to apply the data-centric computing to further develop a scalable memory and storage system architecture for this heterogeneous machine. Nowadays, the machine become more heterogeneous, right? In terms of the hardware, in terms of the processors and accelerators, GPU, the neural processing units, and also including the memory storage, right, and SSD. You have all different kinds of hardware there, and to trying to accelerate the emerging data applications. But how are you able to reduce the data movement? And that is the specific research problem we're trying to attack. And for the short term, we are getting this planning proposal launched, and we're working on submitting a large proposal with other research institutions, Rutgers and Temple, Indiana universities. And we have a new faculty, Dr. Fan Yao, joined the team, and to augment the microarchitecture and security designs. And we are ready to submit a large proposal next week. And for the longer term, my lab is trying to explore more research, education, collaboration efforts with both computing and domain scientists. And we are looking at a new exciting application of virtual reality, augmented reality, autonomous driving, all these different kinds of emerging techniques. We can help to accelerate their data processing. And for the acknowledgement, we appreciate the general support from National Science Foundation, from U.S. Army, Europe program equipment. We have which we have this in-house GPU cluster to manipulate and put in our experiments. And we also sent to a couple of postdocs and graduate student investigation from my lab. And some of the, my PhD graduates already successfully work in the top conference, top engineers, and they get the secured good faculty job. And thank you, and also many other people, reviewers. Okay, thank you. I finished my talk.